Hello and welcome to this GeoStudio webinar on simulating land-climate interactions. I'm Catherine Dompierre and I work as a research and development engineer at GeoSlope. Today's webinar will be approximately 1 hour long. Attendees can ask questions using the chat feature. I will respond to these questions via email as quickly as possible. A recording of the webinar will be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists comprised of several products. The range of products allows users to solve a wide array of problems that may be encountered in these fields. In today's webinar, we will use Seep to assess infiltration associated with land-climate interactions at the ground surface. Those looking to learn more about the products, including background theory, available features, and typical modeling scenarios, can find an extensive library of resources on the GeoSlope website. Here you can find tutorial videos, examples with detailed explanations, and engineering books on each product. Interactions at the ground surface can be quite complex, but are often an important consideration for soil cover design or for determining changes in stability due to infiltration. There are several processes that contribute to water movement at the surface. These include precipitation, snowmelt, evaporation, transpiration, runoff, and then the associated infiltration into the domain, which, as shown in this image, can contribute to flow in just superficial layers or can contribute to deep percolation. The fundamental concept used to evaluate these processes occurring at the ground surface is the law of conservation of mass in the form of a water balance. The Seep land-climate interaction boundary condition provides the ability to assess these processes and how they influence seepage. Boundary conditions in Seep have two general forms. They either represent the independent variable, which is total head or pore water pressure, or the gradient of the independent variable, which is represented by a water flow rate or flux. The Seep land-climate interaction boundary condition falls under the second type, as it ultimately determines the water flux into the domain given the surface interactions listed on the previous slide. We will now review how the Seep solver computes the associated water flux. The equation used by the land-climate interaction boundary condition is a simple mass balance equation. The terms associated with processes at the ground surface, like precipitation and evaporation, are often stated in terms of water depth over a given time period. This ultimately represents a water flux, which typically has the units cubic meters per second per square meter, or cubic feet per second per foot squared. Thus, the mass balance equation shown here is stated in terms of water fluxes. Infiltration associated with a given time step is the sum of the following components over that time step: rainfall and snowmelt, evaporation or evapotranspiration, depending on the selected evapotranspiration calculation method, and runoff. Negative values are associated with evapotranspiration and runoff, as these processes involve water leaving the finite element domain. If the vegetation properties are defined for a Seep analysis, root water uptake is computed below the surface to correspond to the root depth and density. Therefore, root water uptake is not applied directly to surface nodes like the other terms listed here. Should be noted that precipitation is measured on a horizontal plane. Seep corrects the precipitation for the slope angle represented by alpha on this slide. Let us consider how each of these terms are specified or determined for the land-climate interaction boundary condition in Seep Precipitation is specified by the user. This can be done in multiple different ways, including importing precipitation data as a part of a larger dataset, or by copying and pasting data directly into the climate function definition dialog. Precipitation is defined as a continuous function over time in terms of the water flux. This means that the first value defined for precipitation should be at the initial time step, or at t is equal to 0. Water flux is equivalent to a depth per second, which can be determined from precipitation depth measured in a rain gauge over a given period. It's important to note that when the air temperature for a given period is below 0 degrees Celsius, or the freezing point, precipitation is assumed to be snowfall, and so the precipitation defined over that period is not applied to the domain as rainfall. The land-climate interaction boundary condition computes snowmelt when the snow data option is selected in the boundary definition dialog. The water flux associated with snowmelt is based on the change in the snowpack depth from one time step to the next, according to the given equation. The change in snowpack depth for a given time is represented by the first part of this equation and is multiplied by the ratio of the snowpack density to the density of liquid water to determine the associated water flux. In the land-climate interaction boundary condition, the snowpack depth can be defined by the user as a function of time, or estimated by Seep when the analysis solves. Seep estimates the change in snowpack depth over a given period as the difference between the snow depth accumulation and the snowmelt over that period. The snow depth accumulation over a given period is determined by the given equation, where the precipitation during the period given as a water depth is multiplied by the fraction of precipitation occurring as snow, 1 minus the ablation constant, and the ratio of the density of liquid water to the density of snow. The fraction of precipitation occurring as snow is 1 if the average air temperature over the period is less than or equal to the specified threshold, for example 0 degrees Celsius, and is 0 if the air temperature is above the threshold. Snowmelt over a given period only occurs when the air temperature is greater than 0 degrees Celsius. Evaporation is caused by the difference in vapor pressure between the air and the soil and diffusive mixing. Picture a pan of soil that has just been placed in a closed box. Vapor pressure in the soil is a function of the soil moisture content and temperature. Due to the moisture content of the soil, it will have a greater vapor pressure than the surrounding air. This vapor pressure gradient drives the movement of mass, or water vapor in this case, from the soil to the air. In reality, soil is exposed to atmospheric conditions, which also influence evaporation. Wind generally increases evaporation potential, as wind blowing across a surface creates turbulence and enhances vertical mixing of air that carries latent heat, or water vapor, and sensible heat upwards. Vegetation may decrease evaporation by increasing surface friction, which limits wind effects, and by providing shade, which decreases the energy inputted from the sun that contributes to evaporation. Thus, potential evaporation may be dependent on the moisture content and diffusive mixing in the soil, incoming energy, wind speed, and the vegetation soil cover fraction. Modeling evaporative flux at the ground surface requires the determination of actual evaporation, which is based on the potential evaporation. The land-climate interaction boundary condition offers 3 methods for computing evaporation. The first option, user-defined, requires that potential evaporation be inputted as a function of time. The actual evaporation is then computed given the vapor pressure deficit and defined potential evaporation. The second option is the Penman-Wilson evaporation method. This computes actual evaporation from the bare ground surface given the relative humidity, net radiation, wind speed, and temperature. The third option is the Penman-Monteith equation, which computes potential evapotranspiration. The potential evapotranspiration is used to determine the potential evaporation, but not actual evaporation. Thus, this method does not adequately represent evaporative dominant systems and is best used for transpiration dominant systems. For a detailed description of each of these evaporation methods and the associated equations, please see the Heat and Mass Transfer Modeling book available on the GeoSlope website. The land-climate interaction boundary condition can also compute root water uptake if vegetation characteristics are defined. To do so, there are several vegetation characteristics required. The leaf area index is a dimensionless quantity that represents the total area of leaves per unit ground area. The index must be entered as a function of time given seasonal changes to leaf canopies. The plant moisture limiting function defines a limiting factor over matrix suction. When a plant is not incurring any limitations, the factor is set to 1. When the plant's growth is limited, for example by the unavailability of water, the factor is below 1. And when the factor reaches 0, this represents the wilting point of a plant. Root depth is specified as a function of time, given seasonal growing trends. The normalized root density must be specified over the normalized root depth. This function ultimately describes the distribution of roots, or the root shape, from the ground surface to the longest root. Finally, the soil cover fraction represents the fraction of soil covered by plant canopy of each plant. This is inputted as a function of the leaf area index, such that as the leaf area index increases, so does the soil cover fraction up to a maximum value of 1. Given this information, root water uptake is computed by Seep using formal integration across the root depth. As discussed in the previous slides, the land-climate interaction boundary condition requires a number of inputs that represent or are used to calculate the various components of the surface mass-water balance. These inputs are summarized here, based on the selected evapotranspiration method. All evapotranspiration methods require air temperature, precipitation, and relative humidity functions. The user-defined method also requires the potential evapotranspiration over time. The Penman-Wilson and Penman-Monteith methods both require wind speed and net radiation over time, and the Penman-Monteith also requires vegetation height. The gray symbols indicate an optional input, as the snow depth and root water uptake are additional options selected by the user when defining the land-climate interaction boundary condition. The dataset import functionality in GeoStudio assists with setting up all of these input functions used to compute infiltration. The final component of the surface water balance equation is runoff. Runoff only occurs when the computed infiltration results in ponding. The Seep solver initially assumes that there is no runoff to determine infiltration. When this infiltration is applied at the surface, if the surface nodes have a pore water pressure greater than 0, this indicates ponded conditions. The Seep solver then resolves the time step with a pore water pressure of 0 applied to the associated surface nodes. The corresponding water flux represents the actual infiltration into the domain. The runoff is the difference between the initial infiltration value when runoff was assumed to be 0, represented by Qi1, and the infiltration computed when the surface nodes have a pore water pressure of 0, represented by Qi2. We will now review the details of a soil cover model using the land-climate interaction boundary condition. The soil cover model that we will review in GeoStudio is a one-dimensional analysis. The transient analysis has been defined, as have the material properties. However, we will review them when we open the project file. The materials include a layered cover with peat, till, and shale, overlying the protected material, which is a low permeability shale. All of the defined materials use the saturated-unsaturated material model, with functions defining volumetric water content and hydraulic conductivity over pore water pressure. The materials have an activation pore water pressure of -5 kPa, which ultimately sets the initial pore water pressure conditions throughout the domain for the transient analysis. The boundary condition applied to the bottom of the domain is a unit gradient boundary. The unit gradient boundary represents the conditions within the unsaturated zone when the water table is a substantial depth below the surface. We will apply the land-climate interaction boundary condition to the top surface node after defining it. In the soil cover model, we will start by importing datasets into our project file to define the many functions required by the land-climate interaction boundary condition. After importing the data, we will create the associated climate functions. Then we will set up the land-climate interaction boundary condition and apply it to the top of the one-dimensional domain. Finally, we will solve the analysis and review the results, particularly the water balance graphing options in the Draw Graph dialog. I will now open the project file in GeoStudio 2020. The first step for setting up a numerical analysis is to define the project geometry. In this file, you will see that there are two one-dimensional geometries in the project tree. The first has no geometry associated with it. The second one, however, does have a geometry already completed for us. I've done this to demonstrate the ease in which we can set up a one-dimensional geometry in GeoStudio. In the undefined geometry, I can go to Draw Lines. to begin sketching the lines that represent my model domain. I can also go to Define Points and enter the points that define the various layers in the system. These points may also be copied from another geometry in the same project file or from another GeoStudio file. I will go to the Complete Geometry, open the Define Points dialog, select all of the points here, right-click and go to Copy, and then I will go back to my other geometry that is incomplete. Again, I will open the Defines Point dialog, right-click and select Paste. These points now appear in my model space, and I can draw lines between them to create the one-dimensional domain. I will do so by going to Draw Lines. It is important to note that surface layers are not required when using the land-climate interaction boundary condition in SeepW. However, they do provide a convenient approach for creating thin parallel regions. In this case, my geometry is now complete. The second step in the numerical modeling methodology is to assign the appropriate physics to the domain. This involves setting up the analyses in the project tree and defining the material properties. I will open the Define Project dialog to review the details for the analysis that has already been added to our project tree. This analysis is a transient analysis type. Under the Time tab, we can see that the analysis runs for 2 years with 2-hour time intervals, and the results are saved twice per day. The initial conditions and convergence criteria are found under the Water tab. Here, the initial pore water pressure conditions are undefined. This is because we will use the Activation Pore Water Pressure option in the materials definition. Because the materials are already defined in the previously completed geometry in this project file, I can also apply these materials to my new geometry. To view them, I will go to Draw Materials, and then press the Define button. Here I can see that all of my materials use the saturated-unsaturated material model. This was necessary because the water table is a substantial distance from the ground surface, so the entire domain is unsaturated. The materials have been numbered according to their position in the domain. The peat represents the top cover layer. In the Define Volumetric Water Content function dialog, we see that the peat and the other materials use the Van Gunsten function estimation method to define their volumetric water content functions. The peat has a saturated volumetric water content of 0.45, while the till has a value of 0.33, and the shale has a saturated volumetric water content of 0.31. It's important to note that we often choose the xlog option in this function definition window to change the view of the volumetric water content function. If I close this window and then open the Define Hydraulic Conductivity function dialog, I can select all of the hydraulic conductivity functions for all 4 materials by selecting the first one, holding down the Shift key, and pressing the last one. We can see that the peat has the highest hydraulic conductivity, followed by the till, and then the 2 shales. All of the materials have an activation pore water pressure of -5 kPa. This represents the initial pore water pressure conditions throughout the domain at the beginning of the transient analyses. Now that we've reviewed the material properties, I will apply them to the domain. You will notice that in a one-dimensional analysis, materials may only be applied to lines. The peat material is applied to the top region, followed by the till cover, then the shale, with the shale with a lower hydraulic conductivity applied to the largest and bottom region of the domain. Once the materials are defined on the domain, the next step of the numerical modeling methodology is to define the boundary conditions. This will obviously be the main focus of this webinar. In the Define Boundary Conditions dialog, we can see that there is one boundary condition that has already been established for us. This is the unit gradient boundary condition, which is applied to the bottom of our unsaturated domain. As previously mentioned, this boundary condition can be used in analyses where the water table is substantially below the project domain. Now let us create the land-climate interaction boundary condition by pressing Add. Selecting New Hydraulic Boundary Condition, which I will change the name of. Once I've finished naming it, I will change the type of boundary condition to land-climate interaction. When I do so, you will see the list of the required functions that appear in the Define Boundary Conditions window. You will notice that these change given the selected evapotranspiration method. For this analysis, we will use the Penman-Monteith evapotranspiration method, as transpiration is dominant in the system that we are modeling. To populate all of the required fields, I could click on the ellipses button, add new functions, select the type of function from the drop-down menu, and then paste the data into the data table. However, the most straightforward method for defining the climate functions is to import a dataset. To do so, I will close the Define Boundary Conditions dialog, and instead I will go to Define Datasets. Here I will press Add to select the CSV file that I wish to import the data from. I will find my data files, and in this case, I will first select the climate data file. When I press Open, a secondary dialog opens that allows me to select which of the columns in the CSV file I wish to import and what the associated parameter and units are for each column. Once all of my columns that I wish to import are defined, I will press the Import button. The climate data then appears in the Define Datasets dialog. By selecting this dataset, I can view the associated data in the bottom of the window. I will now import my precipitation data file using the same method. You will notice that in this case, the precipitation column is not recognized, so under Parameter, I will change the selection from Do Not Import to Precipitation. The default units of seconds for time and meters for length match with the unit format in the CSV file, so I do not need to modify the units associated with this column. I can now press Import. The final CSV file that I wish to import data from is the vegetation data file. Here I must define the leaf area index column, as well as the vegetation height. I have now finished importing all of the datasets that I will use for setting up the land-climate interaction boundary condition in this project, so I can close the Define Datasets dialog. I will now go back to the Define Boundary Conditions dialog by first going to Draw Boundary Conditions and then pressing the Define button. I will go to my Land Climate Interaction boundary condition, and now I can start populating all of the functions that are required for this boundary. Now when I press the ellipses button beside air temperature, I will complete the air temperature function that I started. First, I will make sure that the linear data point function type is selected. In the drop-down menu beside Dataset, you will see that I can select the climate dataset that I just imported. When I do so, the hourly air temperature data associated with this dataset populates the data table and creates the air temperature function for over 2 years. When I close this function definition window, I can then select the function from the drop-down menu beside air temperature. The next function required for the land-climate interaction boundary condition is for precipitation. I will create this function in a similar way as I did for air temperature. Under the Type drop-down menu, I will select Step Data Point Function. Beside Dataset, I can select the precipitation dataset that I've just imported. When I do so, the precipitation values over time appear in my data table. Back in the main Define Boundary Conditions dialog, I will make sure the new function is associated with the precipitation menu. Relative humidity is defined using the same method. Similar to air temperature, I will select the linear data point function type, and I will use the climate data set. I can now see the relative humidity values in the data table. I will close this dialog and select the relative humidity function from the drop-down menu. Similarly, I will press the ellipses button beside wind speed, add a new function, select the type linear data point function, and choose the climate data set. Now that my wind speed function is defined, I will close this dialog and choose the wind speed function from the drop-down menu. Net radiation was measured at this project site. Alternatively, you may enter functions for solar radiation and albedo over time. If no radiation data was collected, solar radiation can be estimated by pressing on the ellipses button beside solar radiation, adding a new function, and selecting the estimated solar radiation type. Here you must enter the project latitude, as well as a project start date. You may also choose to distribute the solar radiation sinusoidally over each day. Because net radiation was measured, I will select the net radiation option and define the corresponding function. I will use the step data point function type and will select the climate data set. I've now completed setting up all of the climate functions required under the Climate Data tab of the Land-Climate Interaction Boundary Condition. If your site does not experience freezing conditions and you are not interested in vegetation effects, your boundary condition definition would now be complete. However, my project site is in northern Canada, so it experiences freezing conditions and snow accumulation. Thus, I will define the snow data under the second tab. For my study site, I have data on the snow depth over time. Thus, I will use the user-defined snow definition method. However, if this was not the case, I could choose to calculate the snow depth over time. When this option is selected, a number of additional parameters must be specified, including the snow density. The snow ablation constant represents the ratio of the snow lost to sublimation. The daily snowmelt depth is used to compute snowmelt rate for a given time interval. And finally, you must enter the initial snow depth when the analysis begins. Given these inputs, snow depth is computed as the summation of all incremental snow depth accumulations corrected for ablation minus the snowmelt. The snow depth calculation does not require the analysis to be solved, so the associated function can be viewed in the Land-Climate Interaction Boundary definition. Let us return to using the user-defined snow definition method. I will enter a snow density of 70 kilograms per meter cubed, and then press on the ellipses button beside the snow depth function. Here I will add a new function for snow depth, and will use the step data point function type. Here I will select the precipitation data set from the drop-down menu. The snow depth function is now complete, so I will ensure it is applied in the main boundary condition window. I also wish to evaluate the influence of vegetation on water transfer in my domain. Thus, under the Vegetation tab, I will select the Use Vegetation Functions option. Now I must define all of the associated information, starting with the leaf area index. I will select the linear data point function type, and under Dataset, I can select my vegetation data. You'll notice that the leaf area index increases from 0 to 2 during the growing season. This function is only defined over a 1-year period. However, our analysis will run for 2 years. I can select the cycle function option to ensure that the leaf area index function is applied in both years of my analysis. I will now close this dialog and select the defined leaf area index function. The next function we must define is for the plant moisture limit, which describes the moisture limiting factor over matrix suction of the soil. I will select the spline data point function type. You will notice that there's no dataset available for this function. That is because the vegetation dataset only contained the vegetation data that is a function of time. We must create this function by inputting data points in the entry boxes or by copying data from another file. In this case, I will open an Excel file that includes my additional vegetation data. I can copy the data points associated with the limiting factor function and then paste them into the data table. I will modify the generated function so that the line segments are straight. This function is now complete, so I can close this window and select it from the drop-down menu. The next vegetation function represents root depth over time. I will select the linear data point function. Because this is a function over time, you can see that we can import the data from the vegetation data set. You will notice that the root depth was set as a constant value over time. This could have been entered as a single value at the initial time step, and the same value would have been used for the remaining time steps of the analysis. Thus, we do not need to select the cycle function option, even though the root depth was last specified at day 365, because this value will remain the applied root depth for the rest of the time steps in our analysis. I will close this dialog and select the root depth function from the drop-down menu. The next function we will create is the normalized root density function, which describes the shape of the root bulb. We will use the spline data point function option. Because this is not a function of time, I will go back to my additional vegetation spreadsheet and copy the data points and paste them into the data table. As with the moisture limiting factor function, I wish the line segments to be straight. This function specifies minimal roots immediately below the surface, with the largest root density present between 3% and 40% of the total root depth. Below this point, the root density decreases. I will select this function in the main Define Boundary Conditions window. We will now generate the soil cover fraction function. This will be a spline data point function, and again, because it is not a function over time, I will copy and paste this function from my spreadsheet with the additional data points. As the leaf area increases, the soil cover fraction increases and then approaches 1. If you recall, our leaf area index function had a maximum value of 2 during the growing season. This means that the maximum soil cover fraction incurred at our site is approximately 0.78. I can now select this function from the drop-down menu. The final vegetation function that we will define is for vegetation height. We will use a linear data point function defined using the vegetation data set, as the height is specified as a function of time. You will see that the maximum vegetation height is 1 meter during the growing season. We must select the cycle function option, as this function is only specified for a single year, and we want it to be applied in both of the years simulated in our SeepW analysis. I will now select this function from the drop-down menu to complete the Vegetation Data tab. You will also notice that there is an option at the bottom of the Define Boundary Conditions dialog that allows you to specify the minimum pore water pressure applied at the boundary. This can either be calculated by SeepW when the analysis solves, or you can select the user-defined option to specify a function. This allows you to set a limit for the minimum pore water pressure over time. However, I will leave the default selection so the pore water pressure is calculated by the SeepW solver. The boundary condition definition is now complete, so I will close the Define Boundary Conditions window. Back in the Draw Boundary Conditions dialog, I will ensure that the Points option is turned on, and I will apply the Land-Climate Interaction boundary condition to the top of the domain. I will then apply the Unit Gradient boundary condition to the bottom point of the domain. The final consideration before solving this analysis is the finite element mesh, or the discretization of the one-dimensional domain. In the Draw Mesh Properties dialog, I see that the default mesh size is set to 3 meters. I wish to change this to 0.1 meters. I wish to further discretize the regions of the domain that represent the cover system. I will zoom in and click on these top 3 lines and change the edge length such that it is a length of 0.02 meters. I'm now ready to solve this analysis. To do so, I will ensure that the seepage analysis is selected in the Solve Manager and press Start. This analysis takes several minutes to solve, so I will open an identical file that I have already solved. In the results view, I can turn on the flow vectors to see the magnitude and direction of flow through the domain. You will notice that contouring options are not available for one-dimensional analyses. However, the Draw Graph window provides many options for interrogating the simulated results. In the Draw Graph window, you will see a large number of graphs that have already been created for this analysis. The first thing that I do when looking at the results of an analysis is to see if a converged solution was reached. There are multiple plots that can be created to assess convergence. The first one here is a convergence type plot using the results from each time step. From the first dropdown, I've selected convergence, and in the second, I've selected the unconverged pressure head nodes. This graph tells me how many unconverged nodes there are for all of the time steps of my analysis. You can see that a converged solution was reached for all of the time steps since there are no unconverged nodes. The next convergence graphs use the same settings, except it plots the number of iterations required for each time step to reach the converged solution. This indicates which time steps had difficulty reaching a converged solution. The final convergence graph uses the Material Properties option to plot the hydraulic conductivity function. When using this graph to check for convergence, we want to ensure that the inputted hydraulic conductivity function is the same as the computed one associated with the last iteration. You can see that the inputted hydraulic conductivity function for the peat in dark red is the same as the computed one in blue. The same is true for the other materials in the project file. This graph is displayed for a specific time step, so it can be used in conjunction with the other convergence graphs to focus on a specific time step. When the land-climate interaction boundary condition is applied in a SEEP-W analysis, there are additional plotting options available in the Draw Graph dialog. These additional plots can be found under the Water Mass Balance option, which I have used to generate several plots representing the components of the land-climate interaction water balance, as discussed at the beginning of this webinar. The first plot represents the cumulative rainfall applied to the surface node. You will note that there is known rainfall at the beginning, middle, and end of this analysis, as these represent the winter months when freezing conditions are present. If I add the cumulative snowmelt plot onto this graph, you will notice that the periods of snowmelt generally correspond to the beginning and end of the frozen periods when the air temperature is above zero. There are multiple plots here that consider evaporation or transpiration. The first plot shows the cumulative potential evapotranspiration as computed by the Penman-Monteith equation. The potential evapotranspiration is divided into potential evaporation and potential transpiration using the soil cover fraction. Further information on this is found in the Heat and Mass Transfer Modeling book on the Geoslope website. You will notice that the transpiration plot uses data from the nodes associated with the entire cover depth. This is because transpiration or root water uptake is integrated over the entire root depth. If you were to plot transpiration just at the surface node, you will see that it follows a similar trend. However, when compared to the transpiration at all of the cover nodes, there is only a small portion of the total transpiration that occurs at the very top of the domain. The next plot represents the cumulative runoff over time. The runoff computed for this analysis occurs during the second warm season. Given these inputs, SEEP-W computes the cumulative net infiltration at the surface node. I will multi-select the plots related to each component used to compute net infiltration. In this case, I will select the cumulative transpiration just at the surface node, since this is where the net infiltration is computed. This allows for a quick visual inspection of the results. The cumulative net infiltration value appears to be reasonable given the cumulative plots for rainfall, snowmelt, transpiration, runoff, and evaporation. The final water balance plot is for the cumulative deep percolation. This represents the cumulative volume of water seeping from the cover to the underlying shale material. You will notice that the volume of water leaving the bottom of the cover is substantially lower than the net infiltration into the domain. This is because of the significance of transpiration in this system, given the defined routes throughout the cover. Thus, the deep percolation value better represents the water moving into the shale underlying the cover system. The graphing options provide various other ways to interrogate our model results. For example, I have plotted the cumulative change in mass in the cover system in two different ways. The first represents the divergence in flux, or the nodal flow in minus the nodal flow out of the entire cover. These values should be the same as the change in water mass stored within the domain. So I added a second cumulative change in mass plot that shows the change in water mass stored within the cover subdomain. I can plot these two graphs together by holding down the Shift key and selecting them both. You will notice that overall they are quite similar. However, there are some portions of the analysis where the plots do not line up exactly. The difference between these two plots is summarized in the cumulative error graph, providing the cumulative water balance error for the entire analysis. We can also plot the relative error, which is determined by dividing the absolute error by the maximum cumulative change in water mass. We can also create other plots for various parameters with depth throughout the model domain, like the pore water pressure profile throughout the bottom portion of the domain, or the pore water pressure through the cover system. We can also create plots for different parameters over time, like this plot of the pore water pressure at the surface node over time. Further interpretation of the results from these graphs is possible by copying and pasting the data into an Excel spreadsheet. Now that I have determined the infiltration given the land-climate interactions for this one-dimensional profile, I could use this as a surface boundary condition for a two-dimensional or three-dimensional seepage analysis. For example, here I have a three-dimensional seepage analysis. I wish to apply the computed infiltration to the ground surface in the transient analysis in this project. To do so, I will open the Define Boundary Conditions dialog and will add a new hydraulic boundary condition that represents the computed infiltration over time. This will be a water flux type of boundary condition. I will use the function option since the infiltration computed in the original file changes over time given the land and climate interactions. I will define the function by pressing the ellipses button, adding a new function, and selecting the spline data point function type with straight line segments. I now wish to paste the data points into this dialog based on the deep percolation data from my original analysis. You will notice that the deep percolation plot that I have in my draw graph window represents the cumulative volume of water leaving the cover. However, for my three-dimensional analysis, I want to apply the flux values over time. To create a plot with the data I require for my new infiltration boundary condition, I will clone this deep percolation plot and change the option in the second drop-down menu to water flux. This plot shows the water flux entering the domain below the cover system over time. I will then right-click on this graph, select Copy Graph Data, paste this data into an Excel spreadsheet, then copy the data points and paste them into the Define Hydraulic Boundary Conditions dialog in my three-dimensional analysis. The infiltration function is now complete, so I can close this dialog and select my newly created infiltration function from the drop-down menu. I will select the Potential Seepage Face Review option as I will apply this boundary condition to the slope as well as the top surface of my domain. I would now need to open the Build3D editor to apply this boundary condition to the domain before solving my three-dimensional seepage analysis. This webinar reviewed the fundamental concepts and inputs associated with the land-climate interaction boundary condition in Seep. This flux-type boundary computes infiltration into the domain and runoff given the inputted climate and vegetation data. This webinar also demonstrated the dataset import functionality available for assisting in the definition of this boundary condition, as well as the graphing features that allow for the interrogation of the simulated water balance results. I hope that this webinar will assist with your future modeling endeavors. A recording of the webinar will be available to view online. Don't forget to look at the library of resources available on the GeoSlope website. And if you are unable to find what you are looking for, you can always send a message to our experienced team of support engineers by submitting a support request online. We've now reached the end of this webinar. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you are interested in attending in the future. Thank you very much for joining us and have a great rest of your day. Goodbye.